Hi and welcome to MSc. In this video we're going to be looking at solving exponential equations using logarithms. Logarithms are a pretty powerful and cool function that this video is not going to dive into in full. I'm going to specifically focus on a specific feature or trick that we can do with logarithms. And what makes solving exponential equations tricky is isolating the variable that's going to be up in the exponent, because we don't have regular algebraic ways of solving for those or isolating those exponent values. So you're either stuck with trial and error, or another algebraic method that can sometimes work if you have like or similar bases is a change the base method. I did a video on that already. You should check that one out if you'd like. But this log trick that we can do involves the property of logs, where if I take the log of a value raised to the exponent, I can rewrite this as the exponent as a leading multiplier, as a coefficient. And it will become a log to the x. And so this allows me then to work algebraically with the exponent in a normal manner after I've taken the log. Now logs can be quite complex, and logs have different base values, which could be written as a subscript between the log and the argument of the log itself. Typically this is base 10, that's what the default is on your calculator, and there are shortcuts if you know even more log features than what this video will get into. I'm going to work in log base 10, and I'll leave that other properties of logs for study in the future. So we're going to use this log trick, which does seem like a bit of a cheat code, in order to solve exponential equations. So here we have a pretty basic exponential equation. We are faced with trying to solve this. We can't use change the base because there's no way for me to easily express 11 as a base 2 value, like 2 to the exponent of something. And trial and error probably won't work because x is not just going to be a nice whole number here. So we're going to use the log method. So what we do here is we take the log of both sides, because whatever we do to one side, remember, we have to do to the other, otherwise we destroy the equality that was established in the problem. And now I can rewrite this the left-hand side here as x multiplied by log 2 equals log 11. Now we can kind of think in our brains of log 2 and log 11 being kind of like square root of 2 or square root of 11, in the sense that the log is a function itself that's doing an operation to the 2. But we can treat it kind of just as a number. So I can then divide both sides by log 2 to isolate the x. We might not know what log 2 is or log 11, but your calculator will. And so this method will require a calculator to fully solve. At this point now we have x is equal to the ratio of log 11 over log 2. And keep in mind again, as tempting as it looks like you can just cancel the logs, that's not how they work. Okay, it's just like the square root. If I had the square root of 11 and the square root of 2, I wouldn't be able to just cancel the square roots. Unlike square roots though, I cannot just perform the division of 11 divided by 2. Log 11 is a number divided by log 2, which is another number. Now this is written as an exact value because chances are we're going to get a decimal here when we work this out on a calculator. And sure enough we do. We get 3.4594, and then it continues on, and we'll round that. Typically most courses will want 3 significant figures, so we'll round that to 3.46, and that becomes a rounded value. Right? Keep in mind, up here's an exact, here's a rounded, and you can quickly see how trial and error was not going to get you there very quickly at all. So that's a method of using logarithms. We're going to look at a few more examples through the rest of this video and expand some of the algebraic techniques that we need to use to fully solve these. So here we have another one. We can see change the base won't work. There's no way to express these as similar bases very easily. So I'm going to take the log of both sides. So this is going to be the log of 16 to the x minus 3, and the other side is going to be log 5. Just like before, my exponent can come down out front, and I'm going to write this incorrectly for a moment to highlight an issue that I often see with students at this stage of the problem. And so what I've written incorrectly here is that this would write at or read as x minus 3 times the log of 16. But we know that the exponent comes down out front and is a multiplier. So I need to include brackets around this. And this says x minus 3 is multiplied by log 16. That's key. Make sure you put the brackets if you have an expression in the exponent that comes down with more than one term. At this stage then, we see our x that we want to isolate. I can then start to rearrange and solve for it. So I'm going to divide both sides by log 16. That will move it to the right-hand side of the equation by log 16s, which keep in mind is just a number that your calculator knows, and it will move it over to the other side. So I'm left with x minus 3 is equal to log 5 over log 16. And then, of course, I can move the 3 across and make it positive, saying that x is equal to log 5 divided by log 16 plus 3. And just like in the last example, that is an exact value, but we're going to change this over to a decimal. And when we do so, we find that x is equal to 3.58048, and I think it continues on from there. And again, typically 3 decimals, this will round to 3.58. And again, that is a rounded value. So this was a little bit more complex. We needed to have the brackets here and make sure that we kept track of that piece. Otherwise, we would risk having the wrong answer at the end. So let's look at 2 more examples here that are going to highlight a couple other little features as we work through this. So as of right now, based on what I've talked about with logs and what I would expect of my students at this level to do, we have to get rid of any multipliers that we see out front of our exponent factor. So I'm going to divide both sides by 2. If you know more log properties, this step does not become as necessary, although it actually does simplify things nicely. So whenever you see this number out front, you want to divide it out, get rid of it, and move it across the equal sign, as you would regularly when solving algebraic problems. So what we're left here is 7x, and this works out nice. If it didn't, you could just leave it as a fraction, but there it is, the 2,500, half of 5,000. So now this becomes very similar to all the other problems that we've seen. We're going to take the log of both sides, because whatever we do to one side, we have to do to the other. We can bring the x down out front. So x log 7 is equal to log of 2,500. Then we're going to divide both sides by log 7 to move it across to isolate x by itself. And we're getting an expression for x, which is an exact value of log 2,500 divided by log 7. We can write this as a decimal, saying that it is going to be 4.02076 ... and this will round to 4.02. And again, that's an approximate value. I really encourage my students to always write down a unrounded value to start and then round to the appropriate number of decimals. I find the students that do those extra lines there make way less mistakes in their rounding step and are way more likely to round appropriately. I fully encourage you to do that. This last example is slightly more complex with the algebra after we apply the logarithms. And you'll see as we work through this how that's true. So here we have, again, a case where change the base isn't going to work. We're going to apply logarithms. So I'm going to apply the log to both sides. And what makes this one different than the other examples is I have an x on both sides. I have an exponent that I'm trying to solve for on both sides. On the on the left-hand side, I'm going to put in brackets as I bring it down because there's more than one term. And on this side, I'm just going to bring my x down. And so now we have the x on both sides we're trying to isolate. The next move you want to do here, although it might seem a little counterintuitive, is to actually distribute this log 5 into this bracket on the left here. And that's going to generate 2x log 5 minus 3 log 5, and the right side remains unchanged. Now this looks a little counterintuitive. Things look a little bit worse now, right? We've kind of uncommon factored this side. But we wanted to do that because now I can move and collect all my x's on the same side. So I'm going to move this first term across the equal sign and make it negative on the other side. So I'm going to leave my negative 3 log 5 alone. Here I have x log 45. Subtract now 2x log 5. So all my x's are on the same side. That's good. The next step here is I'm going to common factor out my x. So I'm left with log 45, and when I common factor it out of the next expression, it's 2 log 5 that I'm left with. Now, I'm almost done. I have this big bracket mess here, and it's multiplying the x. So if I divide both sides by that bracket part, log 45 minus 2 log 5, that will allow it to cancel on this side and move over into the denominator of the other side. And I'll have isolated for x here. So this cancels with this. And my exact expression for x before we switch over to a decimal is going to say negative 3 log 5 divided by log 45 minus 2 log 5. When you enter this, you want to be careful with brackets in the denominator, depending if you have a natural display calculator or what that might look like on your calculator. We also can't cancel these log 5s because while it's a factor in the numerator, it's not a complete factor in the denominator. This is an exact value, and let's see what it would look like as a decimal. So try on your calculator to see if you can get x equals negative 8.214398, and then I use the ellipse to show that I've not rounded, and it continues on, and rounding to 3 sig figs, we'd get negative 8.21. So the log trick is super powerful. It's an algebraic way of solving for exponents because it brings them down out front. We've worked through a variety of problems here, and if you can tackle this last problem, you're probably ready to go with a lot of the log work that you'll need to do in terms of exponential equations. I hope you found this video helpful. If you have, please consider liking the video and subscribing to the station. And as always, thank you so much for listening and watching.